The minimum redshift I was looking at, minimum redshift equation I was looking at is 2.23, and then the maximum range was about 3.9 of my redshift. But are you saying the separation between the quasar pairs, or?
No, I was actually thinking that, well, the absorber is at some redshift.
Yes.
The absorbers, to get enough of a correlation function to change of redshift, I'm just curious, is around 2, I assume?
Yeah, it's just 2. It goes up, the minimum is 2, and then the maximum is 3.
So I was actually going to ask a similar question. If you go back to one of the slides where you showed the 2 quasar spectra.
Yeah.
All right, so you're saying, okay, I'm going to take the line map forest in this region of wavelength.
Yes.
So is that, do you use the same region for every single quasar pair?
No.
So that it changes?
Yeah, so it changes. It just depends on the overlap. So in my code that I created, I just said that wherever they overlap in the line map forest, that's what I want to take. And so some quasars overlap more in the line map forest because the change in the redshift may be closer, so therefore they'll have more line map forest in common than other ones.
I see.
So yeah, so I'm just in the bottom change of redshift, I set a maximum range is like 0.325 is the maximum change of redshift, and so there might be some that are 0. They might be at the same redshift. I don't know. I'm just taking all these quasars.
So I guess one of my thoughts for maybe reducing some of that scatter is breaking it up into what redshift does the line map.
Yeah. So I was gonna show that to you as well, but yeah, I wasn't able to produce that plot.
Oh, that's fine.
Yeah.
But yeah, that's something you can do next to maybe try to tease out.
Most definitely. See how it changes the correlation from the change in the redshift.
Any other questions?
I was kind of wondering what the data does it apply to? So the old payment was individual spectrum of better quality.
Yeah. So
this is okay.
yeah, I can. It was listed in yeah. So so I took the mean of all their signal to noise ratio. They had like a 23.92, and mine was about 4.79. My signal to noise ratio is like SES. Their spectra are they're not too high signal to noise. So that's why. So my first thoughts were like, I'm getting this wide spread because I get horrible data, and like the majority of them. So like I have some data, some spectrum that ranges at like in the 40s signal to noise ratio, but the majority of them are very, very low signal to noise ratio. So maybe I might want to try to, I don't know if that will bias my data, but if I just take off all the low signal to noise ratio, only plot the few high signal to noise ratio, we'll probably see if I get a similar
I would be wondering, if you will kind of lower your signal to noise ratio in steps and look.
Yeah, look how it changes within.
Yeah.
Okay. So bend in with signal to noise ratio as well.
Yeah. Just as a data exploration, I have no idea what this is going to result of an idea of what to try.
Most definitely.
If you have 2 quasars that are very close to each other and there could be several absorption systems in the line of sight, right? And so some of them could be correlated because they're big with the enabling quasar, and another cloud could not be correlated because it's small.
Mm-hmm.
So shouldn't you chop up your sideline to try to identify individual components that overlap instead of just cross-correlating everything?
I don't think I understand. I'm sorry. Can you repeat that question? I don't think I understand.
So if you have, let's say you have 3 absorption systems in one quasar and 2 in the other, what would your Flux correlation say to that?
If that might be a case, that might be a case for a few of those quasars. So since I'm using such a big amount of data, and please tell me if I'm not answering this correctly, but if I'm using such a big amount of data, like I'm taking the average of all those, so that may be the case for some of them, but that's not the case for all of them.
Sure, but you expect that there's going to be a size distribution in clouds, right? So
yeah,
all of them are going to have, the further away they are, the higher the likelihood that only some of the systems overlap.
Yes.
So I mean, you didn't show the formula that you actually use for your correlation.
So the formula is right. It's right here.
Oh,
yeah. Sorry, I didn't point that out. But this,
okay,
this is a longitudinal function that I use. My function is the transverse mean that delta b is equal to 0. So if I just said delta b is equal to 0, because I'm not taking into account that they are redshifted. So this is a function that I use.
But you could have, if you had 3 absorber systems in one line of sight, you should really have 3 correlation coefficients because they might be independent. The sizes of the clouds are independent, so that you would get different correlation coefficients depending on which system you look at.
All right, well then I will plan on putting that inside and try looking into that. I don't know the answer to that now.
With the alignment off the course, can you say for sure how many clubs you have?
I don't know if you can
I
tell.
have my impression that it was too ragged to really pinpoint particular.
Well, at least I'm not saying I have a solution. I have a question. But in things that are you put everything in one number. If it's well correlated at 3 at z equals 3 and uncorrelated at z equals 2, you'll get a number that shows you very low correlation. Whereas if you did it from z equals 3 to 2.9, you might find a high correlation. That's similar to putting it in redshift bins. But there might be a statistical approach that doesn't do like strict redshift bins, but has like some fuzzy Gaussian weighting, for example. I mean, there's several ways you could set that up, but I see that if you have many systems if you have many systems and you expect a size distribution, then this is always going to give you an average.
Yeah, most definitely.
And it's going to, your correlation is lower. It's going to be lower if you have more systems in your line of sight.
Yeah, I agree. So yeah, I'm not gonna.
So it's not unbiased.
Yeah.
I wonder if simulations could give you a handle on that problem to a certain degree, about how big an impact will sort of
The size,
yeah.
I think that was the last item on your to-do list.
I see.
Yeah.
Let's do simulation.
That could be
Same
a,
thing.
that could be a thesis, I guess.
Well, there's simulations which have that already, right? You just run the questions through.
That's right, yeah, exactly.
But I suppose it's not as easy as just run the equations in the simulation. It never is, right?
I don't know exactly what the illustrious people have done and what the data production is.
None of us in here knows.
It might be worth asking.
For sure. Well, I'm at heart with the people who made it, so I should probably go talk to them.
All right, well, thank you. If you want to talk to us after